Welcome to Wireless Future. I'm Emil Björnsson, and as always, I'm here with Eric Larsson. How are you today?
Oh, hello, Emil. Good. How are you?
I'm great. And I'm looking forward today to talk to you about antenna arrays. So, what is an antenna array to you?
Absolutely, Emil. So, antennas. Well, to start with, an antenna could be a lot of different things. I mean, sometimes the textbook is just little like dash or something in the figure, but in reality, of course, it could be a monopole or a dipole, or it could be more commonly a patch antenna. And then when we speak of antenna arrays, then we simply mean antennas that sit together in some arrangement. So they could sit like, it could be two of them like this, or it could be any number basically. And the antenna array itself could have whatever geometry. I mean, the most common is that the antenna sit in a linear array, and then they're simply spaced along a straight line. It's very common that the spacing is uniform, and it's also very common that the spacing is half a wavelength for good reasons. But there are lots of other kinds of antenna arrays. For example, one can build planar arrays, and then they all sit on like a planar slab with typically uniform spacing, but not necessarily so. And these antennas that sit in an array, then they all cooperate and act together, which is a concept that also underpins much of the physical layer in modern telecom and wireless standards, specifically in 5G, where the antenna array technology that's used, it goes under the name Massive MIMO, which of course you, Emil, has been a pioneer within, and also written a lot of papers and textbooks. And maybe you want to take over and tell us a little bit, and tell the audience a little bit about Massive MIMO specifically.
Right, yeah, I can do that, even if I think you are as much of a pioneer in that topic than I am. But yeah, I think one aspect to the whole thing with having antenna arrays as compared to having one very huge antenna is that in addition to filling a particular area so that you can collect more energy, typically the more area you have, the more energy you can collect with your antennas, you also want to be able to observe the world more carefully. So in massive MIMO systems, the idea is that we have an abundance of antennas. We have very many antennas compared to something, in this case compared to the number of data streams or different beams, signals we send at the same time, at the same frequency in different directions. So the number of antennas should be greater than the number of users. And there are theoretical reasons for this, and there are practical reasons for this kind of design. But one way to view it is that when you have an antenna array, you can send signal different direction, and that's like aiming signals towards different squares on a chessboard. And then if the number of pieces that you have left on your chessboard is relatively small compared to the number of squares you have there, then there is a small risk that if you just put them out randomly, some of them will collide with each other. There should be a good chance that there is some space between each piece, and that makes it easier for you to sort of send focus signals towards them. And this is what Tom Rosetta was calling Massive MIMO when he sort of invented this idea. And nowadays in 5G, we typically have base station with some 64 antennas, and we have 8 users at most that we are serving at the same time.
So basically you're saying we got all these antennas in the array, and they can act coherently together so as to form beams, so that we can shoot one beam at the first user, a different beam at the second user, and so on. And then we just got to make sure, and with some luck, hopefully, that these users aren't too close to each other so that the beams don't collide. You said 64 antennas. I used to think it was 128 in the main vendor product line, Massive MIMO units. Is that 64 or is it something else?
Actually, 64 is the maximum number of antennas that they have. There are 32 products as well. Then one should keep in mind that sometimes they are mentioning the number of elements that exists. And these are, for example, the patches that you are mentioning. So one antenna, as we call them, might actually consist of multiple elements that just act together in order to form a particular directivity. But that's more going into the antenna design.
I see. So you're saying that there are like 64 digital or RF streams that eventually get digitized and then processed.
Right. So when we as communication or signal processing people are talking about antennas, we are viewing it from what is it we can control in our computer when we are designing the signals and when we are receiving the signals. And then what's actually going on in the electromagnetics might potentially expand the number of elements somewhere in your hardware design. That's just in order to fill the space where you can put out your elements.
Sure, but I mean, I feel the interesting question is how many digital streams, how many like parallel digital streams can get fed to the array simultaneously, and that would be 64 then in these products, as I understand you.
And when people started to work with this type of MIMO technology, it was either called space division multiple access, because you were having different users at different spatial locations and set them at the same time. Nowadays, people often talk about multi-user MIMO, where MIMO stands for this multiple input, that is the antennas on one side, and multiple outputs that are the users on the other side. And in the beginning, people were thinking that, okay, you have a certain number of antennas, this is the number of digital streams, as you were saying, and the maximum number of users you could serve is equal to that number of antennas. And you, of course, want to send as many signals as you could. And in theory, that is kind of the limit. But then it turned out that it is in practice very hard to send as many digital streams as you have antennas, because then everything will collide. And it will be very hard to build this. So this is why Tom Rosetta was coming up in around 2010 with his massive MIMO setup. When you are building the whole system in order to send fewer data streams than you have antennas, and have this abundance of antennas to achieve this.
Right, sure. So I mean, the intuition there should be clear, right? You want a lot more antennas than actual beams that you form, because if you form too many beams, then the likelihood that some of them will collide goes up. And 64 antennas, and did you say 8 simultaneous beams that you could form?
Yeah.
I mean, 64 doesn't sound that much to me. I would expect at least a few hundred, but maybe in the future we'll be getting that. So now with massive MIMO technology, so the idea is to have a lot more of antenna elements than beams do you actually shoot at the given time. But you also need to know in what directions to shoot these beams. And that's what in comm theory we call having channel state information. And to me, really what makes massive MIMO work so wonderfully is that this channel state information can be obtained by exploiting electromagnetic reciprocity, so that each and every terminal sends a pilot waveform. And this pilot waveform is received at the array by each one of the antennas. And then each one of the antennas estimates the channel impulse response to that from that terminal. And then by reciprocity, we know that this response is the same in both directions, so the same on uplink and on downlink. And that can be used then to compute how to shoot these beams on the downlink. Yes. So
you associate massive MIMO with this reciprocity approach, right?
Oh, 100%. I mean, to me, massive MIMO means two things. Number one, an excess of service antennas. So on the order of 5 or maybe 10 times as many antennas at the base station as you shoot beams that you shoot simultaneously. And number two, reciprocity to get channel state information.
Right. And I think this is certainly the ideal way of building things. Then there are MIMO systems operating in situations where you can't use reciprocity methods that you were describing. And one particular reason for this might be that you have one frequency band when you're transmitting down to the users, and one other frequency band where you are transmitting from the users up to the base station. So then you can't really utilize reciprocity.
No, that's right. So you mean FDD operation. I mean,
yes.
What I said about reciprocity, of course, applies mainly to TDD operation, where you duplex uplink and downlink in over time. Sure, but in FDD, the story is a little different, and then reciprocity doesn't hold, so other techniques are needed to get this channel state information.
Yeah, and then it will be a difficulty to have a lot of users that are moving around quickly in a complicated part of the world, in the city, for example, where there are very quick variations in the communication channels, and do this in a system where you can't use reciprocity. Because, yeah, if you want it to work in those situations, you typically need something to be a little bit simpler, such that people are not moving very quickly, so you have more time to figure out the channels, or that the environment have some simple features, such as you have a so-called line of sight channel where the base station sees the user directly, and then the channel is not varying as quickly over the frequency domain.
That's right. I mean, sure. I mean, if you got line of sight to all your users, then in principle it'd be enough to estimate the angle, maybe the elevation and azimuth to the users, and that would be it. I mean, you wouldn't need the complete impulse response from every antenna element in the array, and then there might be other ways that could compete with the reciprocity to get this channel state information. So I want to talk to you, Emil, about the actual antenna array itself and what it looks like, and specifically its topology and how to place the antennas within the array. Because to my understanding, in the main 5G products from the, let's say, leading 5G equipment vendors, these panels are all like rectangular panels with small patch antennas that sit uniformly spaced on the grid. And you have recently published a paper entitled From Antenna Abundance to Antenna Intelligence in 6G Gigantic MIMO Systems, where you explore or really question this, let's say, design assumption that or question this design concept where antennas sit uniformly spaced in a rectangular grid on a panel. So why would we want to do anything else?
Right, that's a good question. And the starting point was really what you alluded to earlier, that why don't we have more antennas in our systems? Why don't we have hundreds of antennas? And if we look back a bit in time, then in the 4G system, there were typically 2 to 4 antennas. And now we have 32 or 64 antennas in 5G. And if we continue scaling in similar manners, we will have hundreds of antennas in the next generations. But what is the reason for adding these extra antennas? Well, it is because we want to shoot more beams so we can serve more use at the same time. But if we then have some 4 or 8 times more antennas than we are sending beams, then the number of antennas that we need is growing very rapidly with the number of use we want to serve. And I started to think about, could we do something where we could still serve more antennas in future systems, but maybe not need as many as or scale the antennas as quickly, so that we keep this kind of 4, 8, 10 times more antennas than users.
Yeah, I mean, totally. If we want to shoot more beams simultaneously, we want more antennas to maintain this massive MIMO ratio between number of service antennas and number of beams that we shoot. But isn't it always also that we want more antennas to get a better link budget? Because the more antennas on uplink, the more power it will soak up. On downlink, the more antennas, the sharper beam we can form, and the better link budget we can get, or the better SNR. So there are really two reasons to increase the number itself here.
Right, that's certainly the case. And it's often so also that a base station that is transmitting the downlink, there is a regulation on how strong is the signal allowed to be in a particular direction, which is like the main direction pointing perpendicularly from your antenna array. And when you're building your array, you want to make sure that you can reach the maximum value in order to provide the longest coverage in your system. But there is a number of different factors that is determining that maximum value. It is the total transmit power you have, it is the number of antennas that you're using, and it's the sort of gain, the directivity on the individual antennas. So if we are cutting down on the number of antennas a little bit, then we will have to compensate by increasing the power in total, or play with the gain of the antenna. So there are ways of maintaining the link budget.
Yeah, sure. Of course, that sort of interplays there. But at any rate, let's focus on the topology of the array itself. And maybe to start with, let's get back to basics. If we build an antenna array, let's say it could be whatever, it could be a planar, it could be a linear, it could be anything. Let's say it's a linear array. Does it really matter where the antennas are located? So for a given aperture, so let's say I can afford an aperture of whatever, 0.5 meter long, and I can afford 10 antennas, let's say. Does it really matter where I place these antennas? I mean, the conventional wisdom is that they should be spaced half a wavelength apart, but does this matter? Could it be like spaced more sparsely or more densely or just randomly, or does this make a difference?
Right. So it depends on what you want to achieve with this antenna array. So if we start from the most basic feature, you want to transmit from this antenna array to one user located somewhere, then the first thing you want to make sure is that your antennas are sort of, they typically have some directivity, some directions that it prefers compared to others. And then you want to aim that directivity roughly towards the user so they don't look away. And then what you want to do is that the signal from each of the antennas, you transmit the same signal, but you delay them or phase shift them differently so that they are reaching the receiver in phase with each other. So they don't need to be in phase when they transmit, they should be in phase when received. But apart from that, you can have any arrangement of the antennas when you only want them to be reaching the user. And this is basically what we call beamforming. We send the same signal with different phase shifts, they add up, and with that is basically creating a beam over the air aiming towards the receiver.
Absolutely.
So that's a situation where it really doesn't matter how you put out the antennas in this area where you're allowed to have them.
Sure, because I mean, with beamforming, basically what matters is the signal to noise ratio at the receiver, the link budget to the receiver, and that will be dependent only upon the number of antennas that we have, because they all act coherently together, so the amplitudes add up with a proper phase. Now, in practice, there will be other considerations also to make here. One, of course, will be mutual coupling among the elements, so you probably don't want to put antenna elements closer than half a wavelength, generally speaking.
Yeah, exactly. So that is one reason where this half a wavelength thing comes from, that if you put them close to each other, they start to electromagnetically interact a lot with each other. Yeah. And then it might be that, my whole example of sort of the signals can be transmitted and just added up, they're acting sort of independent of each other. That kind of assumption breaks. And then it's typically worse, but it could be better. But let's not go into the details on the coupling, but stay away so you are further away than half a wavelength.
Yeah, so if they sit further away or at least half a wavelength apart, then coupling is manageable and at least not a detrimental factor to the array performance. So how is it then that typically arrays are built with half a wavelength of spacing? I mean, we just agreed that from a link budget perspective or from an SNR at the receiver point of view, it doesn't matter where they are placed. So how is it then that typical designs of today are built upon a lambda half or half a wavelength spacing?
Right. So this has to do with additional considerations that comes if you have more than one user or more than one data signal that you would like to consider at the same time. So when a signal, it's easiest to think about it that it comes from a particular angle towards your antenna array, then it arrives as a wavefront that is sort of sweeping over your antenna array, and then it will hit the different antennas with a little bit different delays, and you will see this in terms of different phase shifts in your signals. And then if you want your antenna array to be able to distinguish between in which directions or how does the signal arrive to you, then it comes down to that you're actually having a continuous wave that arrives to you, and you have antennas that basically take samples from this. And then one could apply classical things from the Nyquist-Shannon sampling theorem, and that will eventually come to the conclusion that exactly lambda over 2 spacing is the best spacing there, because then you're sampling your signals so that you extract the most amount of information of them.
I see. But now this assumes a line of sight channel, no? This argument that you just made assumes a line of sight channel to the users. Is that accurate to say?
Yes, exactly. So in that case, I was discussing having some different plane waves coming in from different angles, and you want to distinguish between them. So that could be a line of sight channels, signals coming from different sources. It could potentially be a multipath environment where each plane wave comes in from a different direction as well. But one can extend this kind of argument to a multipath environment, and the most commonly considered situation in textbooks is what we call isotropic scattering. The idea is that the user sends a signal and then it bounces on a big variety of objects so that the signal arrives to the antenna array from all angles equally likely. So it's just a random arrangement of plane waves coming from these different directions. And then the typical textbooks examples then reaches the point that you will have some mathematical or statistical correlation between how the channel looks like at different points, but if you put the antennas exactly half a wavelength apart, that correlation will be 0. And otherwise the correlation is called sinc function, that is becoming smaller with distance. And that is also an argument,
Yeah, I see. So you're suggesting that if you got an isotropic scattering, then the fading coefficient will be random. And if you put the antennas, if you measure the fading coefficient at 2 different points that are half a wavelength apart, then the fading will be uncorrelated.
Yeah.
So that sounds like a good thing. I mean, insofar we care about uncorrelated fading.
Yeah, and I mean, it's called fading because the signal quality goes up and down, and it's of course good if it goes up, but the bad thing is when it fades down, and therefore to minimize the risk that happens over all of the antennas simultaneously, then you won't like to have this uncorrelated or independent fading on different antennas.
Right, so as to maximize the diversity gain of the array or maximize the channel hardening that you see in the MIMO processing. I mean, this became a rather intricate technical argument, but it sounds like there are some fundamental reasons for why a half a wavelength spacing is good to have in an antenna array.
Yeah.
More or less irrespective of the propagation environment, because you mentioned both line of sight here, and then you mentioned isotropic fading or isotropic scattering, which is really the opposite of line of sight in a way. So now, if that's the conclusion, that half a wavelength spacing is actually quite good, if not optimal, then it sounds to me that current designs are actually very good. So what is your new paper about them?
Yes, so it sounds very much as the current designs are good, because in these 2 very textbook-like examples, it is the best thing you can do. So that's why people have been taught and believed in this. But the thing is that the real environments that we come across when we are deploying our base stations are not exactly matches with any of these different examples. So if you have line of sight users, it's typically so that a base station is deployed on a rooftop or in tower, and it's not meant to cover the entire world, but you have a limited sector of some 120 degree where the users are going to be, so 1/3 of the world, and that is horizontally, and vertically all the users are below the base station. You typically don't have users above it, so that is also changing things. And when it comes to the multipaths, since you place your base stations at elevator locations, often the multipaths happens around the user or at some major objects in the environment, and when the signal are arriving towards the base station, it doesn't come uniformly from all angles. It comes from a particular set of angles. And this is creating some structure that we can utilize and build arrays that are better at extracting that specific characteristics.
But that's quite interesting indeed. I mean, so are you suggesting that this air quotes optimality or near optimality of half wavelength spaced arrays, well, that holds for certain line of sight scenarios, it holds for isotropic scattering, but in practice we have neither of them. And then there is an opportunity here now to actually optimize the spacing within the array itself.
Yes, exactly. And if one follows the same kind of theoretical practices that we did with those two examples before, but apply to this new situation, the conclusion will be that now you would like the antennas to be further apart to be optimal using the same kind of arguments. And as soon as you say, okay, now I will put my antennas maybe one wavelength apart instead of half a wavelength apart or something like that, then you also have the possibility of not putting them out uniformly anymore. Because we were saying you never want to be shorter than half a wavelength because then you get a lot of coupling effects. Yeah. But if you can move them around and have something more asymmetric without running into that mutual coupling problem, why not use that as a design dimension as well?
No, absolutely, 100%. I mean, but still, I think this might speak against the intuition of a lot of people, and including myself, because somehow if you got an aperture, let's say I can afford an aperture of 0.5 meter, let's say, for whatever reasons, could be that just because of physical space or aesthetic reasons or something else, then wouldn't I want to fill this aperture with as many antennas as possible? And then, since we know that, we don't want to put antennas closer than half a wavelength together, but I still want to fill the aperture as much as possible. And from that, it would follow that to pack in as many as possible. That means half a wavelength spacing.
Yeah, that makes a lot of sense, but the problem is that it is also associated with cost and weight and bulkiness and things like that. So you were mentioning earlier that actually a 5G base station might have 128 elements, but we only say that it has 64 or 32 antennas, and that is exactly for this reason that if you would put in enough radio hardware so you can control every element individually, you would increase the cost and the weight and bulkiness of the whole thing. So they have already started to play with the right kind of trade-offs there. And now I was thinking about in a 6G system, if you would just scale things up and have some 4, 5, 6 times more antennas, then the bulkiness would grow as well, and maybe we could utilize this non-uniformity in the arrays so that we can get similar performance, but with a little bit fewer antennas, maybe cut down on this antenna user ratio from 4 or 8 to 2 or something like that.
Yeah, but that's kind of cool. So really the design problem now is that, okay, given an aperture size and given a permissible cost of the system and given a permissible or maximum number of antennas, what is the best way to place them within this aperture? And then lambda half spacing might not even be an option because we don't have enough antennas to put them with lambda half spacing. So we got to put them either more sparsely apart or non-uniformly or randomly or something. And then you're suggesting that here is actually an optimization problem that we can solve.
Exactly.
Even for a specific propagation environment. So let's go there. Now, if we do this, so we put the antennas non-uniformly over an aperture. What are the beam patterns going to look like? Right.
So if one opens a textbook and say, let's build a uniform array, but with an antenna spacing that is larger than half a wavelength, what is going to happen? Well, the total aperture length, so the distance between the outmost antennas, that is determining how narrow the signal is going to be. So you shoot the beam, it has a perhaps cone-like shape, and the radius of that shape is determined by how long the array is. So longer it is, the more narrow it becomes. But since you still have a total amount of transmit power that you're sending out, then it needs to go somewhere. So if you aim it in a more sharp way towards your receiver, then there will also be some leakage in other directions, and that one is having some kind of shape. And the more narrow the signal is, the more, and particularly when you have a sparse array, larger than lambda over 2 spacings, the side lobes, as these other directions are called, becomes larger, and there is a concept of grating lobes that can also happen. These are side lobes that are indistinguishable from the direction where you would like to transmit. So you send in one direction, and then you have an equally strong signal going in another direction.
Sure. So basically what you're saying is that fundamentally, let's say that we start with half a wavelength spaced uniform linear array, and then we stretch the aperture, okay? And then, of course, we can't maintain the spacing between the antennas, but we stretch the aperture, and then we just place the antennas a bit kind of at random within that aperture that we have gotten. In general, then the spacing will be larger than half a wavelength. Then what will happen is that, well, the main lobe in your beamforming, the magnitude of the main lobe will not change because it's always equal to your m squared in power. But that main lobe will get narrower because the aperture is larger. But to pay for that, you also get side lobes, grating lobes that point in other random directions, which could be bad, of course, because there could be somebody out there whom you're shooting interference at inadvertently. But does this really matter? I mean, with grating lobes, because in all the MIMO theory, we know that with, let's say, maximum ratio beamforming, then it's only the number of antennas and the path loss that matters. And for multi-user beamforming, a lot of times we just evaluate performance on random statistical channel models. And will these grating lobes make a difference in practice?
Right.
I thought not really, yeah.
Well, it certainly depends on what kind of propagation environment you have and the situation there. So you could be in an unlucky situation where the grating lobe creates a lot of interference aiming accidentally exactly towards where another user is located. And then you come into a situation where what should you do? Either you don't transmit very much to your intended user, or you create a lot of interference. How do you deal with those kind of situations? And I would say that in a single cell situation, you only have one base station and a couple of users, you can still deal with interference. You are in control of everything. You can tune your beams so that you might be dealing with some of these issues. But people are usually concerned with grating lobes in array design because it is either bad for sort of interference that you're hitting some other cells or other systems around, or if you are building arrays that are also going to be used for so-called angle of arrival estimation. You would like to localize from where did the signal come to aid some, Google Maps or some other application to sort of tell you where is the user. Then it's problematic if it's either this direction or it could have been this other direction that it looks the same. And this all comes down to this sampling theorem that we talked about earlier. People who are familiar with that one knows that if you sample too sparsely in time, then there are multiple signals that look the same. They are the aliases of each other's. And the same thing happens if you're sampling in space too far apart. There are signals coming from different angles that you actually can't tell apart.
Sure, 100% on the angle of arrival estimation. I mean, because having grating lobes wrecks your ambiguity function, so that can be pretty bad. But from a communications perspective, with spatial multiplexing and beamforming, it seems to me that these grating lobes aren't necessarily that much of a big deal, because I mean, you do get the grating lobes, but you also get a narrower main lobe, which means that the likelihood that somebody else is very close to your targeted user and would fall in the same main lobe, that chance also reduces. So there's a complicated trade-off here between, you might create some interference in some other random direction, but you're certainly also creating less interference in directions that are very close to where your targeted user lies.
Right, but here comes the interesting thing then, that when you have stretched your arrays out to a particular length, it is the distance between the outermost antennas that determines how narrow your main lobe, your focusing is. But the exact direction or exact location of the antennas at the inside matters as well, and they matters in terms of deciding how does the pattern look like in directions that are not the main direction. So if they are exactly uniformly but sparsely deployed, you get this grating lobe effect. But if they have some other shape, you can get a different shape of the signals. And if you're tuning the locations of the antennas in the right way, you might actually get that the signals that are not in the main lobe are spread almost uniformly over all of the other angles. And that can be beneficial for a system.
Totally. I think that's a very important point indeed, that the width of the main lobe is chiefly determined by the extent of the aperture. So the distance between the leftmost and the rightmost, let's say, antenna. Whereas the appearance of the grating lobe pattern will depend on the arrangement of all the antennas that lie in between of the leftmost and the rightmost. So is that the way to mitigate grating lobes? Now, insofar grating lobes are a problem to start with, is the way to mitigate them to just place the antennas randomly within the aperture? Or is there something else that one could do?
So you could put them out randomly, and then you get some other patterns that are unlikely to have specific grating lobes. If you define this as a beam direction that is a side lobe and equally strong as your main lobe, well, then that will most likely not happen. But you can actually design the antenna locations and optimize them even further. And people have been studying this for a long time in space observation situations.
Yep.
So this is a situation where you put out big antennas that you aim towards the sky, and you might find some area far from the cities where there will not be much electromagnetic interference from anything. You're not really constrained in terms of the land area where you can deploy things. You're just constrained about how many antennas you can put out there. And there people started to analyze for more than 50 years how to position the antennas so that you could sort of see things coming from different directions in space, but still mitigating the side lobes or these grating lobes.
Sure. I mean, I was just about to say that design of array topologies is a very old topic. And now maybe what makes it a little different here for the 6G systems is that the metrics are different. I mean, it's a different thing to optimize an array for spatial multiplexing and massive MIMO as compared to optimizing an array for radio astronomy or something where you're looking for like a distant star or some radiation from space. So what metric would you recommend, or what metrics have you been using in your papers for optimization of the array topology for the 6G MIMO context?
Right. So we started to look into what were the metrics people were considering in these older papers about array design, which were more about localization or sensing. And there they were focusing a lot on sort of starting from an antenna array that had this lambda over 2 spacing, and then taking out antennas and do it in a structured way to remove what they call redundancy. And the easiest way of thinking about this is that you have a ruler in your home that you can use to measure distances. And there you have markings every, say, centimeter or every inch. And so then you have a marker at 0, at 1, at 2, at 3, and so on. And there is a lot of redundancy there, because if you would like to measure something that is, say, 2 centimeters apart, you can measure between 0 and 2, or between 1 and 3, or 2 and 4 and so on. So things are repeating there a lot. In principle, you could delete some of the markings along the ruler, and you would still be able to measure any centimeter distances that you like. And they use the same kind of principle to put out the antennas, delete some of them that were redundant. And here, the sort of intuition behind this is that when signal arrives from different angles, then the way of determining what angle it came from is to compare the signal at a pair of antennas and see how is the phase shift or delay between them there. And if you have multiple antennas that are at the same distance apart, they basically provide redundant information, so you can delete one of them. So that is how they build this kind of minimum redundancy arrays.
Sure, to me this sounds like if you got an array and you want to use the array to determine the angle of arrival to some object, then the camera bound will essentially be determined by the length of the aperture, whereas the ambiguity function will be determined by like where the rest of the antennas are positioned. And there you would like to position the antenna so that you can measure every, as you said, every pairwise distance is represented. But now in the context of designing MIMO arrays for 6G, is it better than to start with a uniform grid and remove antennas? Or could it be better to just say, hey, we can place them anywhere. As long as they are at least half a wavelength apart, let's just place them anywhere. They don't have to sit necessarily on this nominal uniform grid. They could be anywhere. Is there a benefit to going beyond the kind of like grid-based thinking at all?
Yeah, that's an excellent question, and that was what we were exploring. So we, in the paper that we referred to earlier, we were considering both the approaches of sort of starting from a very dense, large array and then removing antennas one after the other, trying to maintain performance. And what performance meant in the communication context was that we said, here is my base station, here is my propagation environment, and let's generating 10,000 different situations where users are located there and create their channel conditions. And then trying to optimize our array for some performance there, such as the average data rate that you can deliver to your users. So then we did this both by sort of starting with the grid approach, taking out antennas, trying to maintain as large average data rate as possible until we came down to the number of antennas we could accept to have. Or we developed a concept that we call the pre-optimized irregular arrays, or PIA, where we put out the number of antennas that we wanted to have in the array. And then we move them around in the software and try to figure out what were the right locations to place them at.
When you say move them around in the software, you mean they could be arbitrarily placed, right? So not necessarily on this uniform grid.
So in that case, there were no grid location. And then we optimized there also for the average sum rate. And as one could imagine, when you take away a requirement such as they need to lie on the grid, you can do a little bit better, but because we were optimizing for a certain situation, but it turned out that the gains from leaving the grid was very small. So I think a grid placement also works out. On the other hand, if you're gonna anyway just compute an antenna array and then go out there and put them out and let someone place them there on the grid somewhere, or not on the grid, but just measuring it with some other methods, it doesn't really matter if it's a grid or not.
It might even might look nicer if they are at least, I mean, that the locations fit on a uniform grid. Who knows?
Yeah.
But so did you say that you optimized this for like some specific propagation environment? Did you have measured channels that you started off with, or how did you evaluate performance in them? Because it seems to me that the conclusions here might be a lot dependent upon the specific scenario that we encounter.
Yes, so I were approaching this as if it was a site-specific optimization. So you are a telecom operator, I decide, here I would like to put my base station, what shape should it have? And this is similar to how I know that telecom operators are already working when they decide on how to position or rotate their antennas and so on. They are using some software to predict what performance they will get with different parameters. Then it might be how they should rotate it and how they should tilt it up or down or things like that. But now you could also sort of, for a particular environment, optimize the antenna arrangement and do this for every site specifically.
Totally. So totally. But okay, so here's the question I've been sitting on for some time now. If you got your, let's say, you got the nominal uniform grid, okay, and then you thin this out using your advanced optimization algorithms, and then you measure performance through some metric, let's say some capacity maybe or something like that. How much better is this compared to random? Let's say that I start with my uniform grid, and then I just thin it out at random by removing antennas at random until I get the desired number. And then I get the design. And then I try this 100 or 1,000 times maybe, and I pick the best. How much better is your algorithm as compared to just the best of 100 random realizations?
Right. I think it will depend on what kind of propagation environment you're having there. The random one was interestingly better, substantially better than the uniform sparse array. But
also uniform sparse now means that the spacing is necessarily larger than half a wavelength.
Yes,
right?
exactly. So if you start from a small array with, say, 16 antennas, or 4x4 array, and then you stretch it out, you do better. Then you randomize the antenna location that's inside, you do even better. And then you apply our optimization and you do further better. And I think depending on the situation there, we could get something between 30 and 50% better performance by positioning them accurately as compared to randomizing the locations.
Oh, I see. Cool. Okay, wow. So there's also this concept, which is a bit related, I think, with, on one hand, antenna selection. That was very popular some years ago, at least in academia, with the idea is basically that you have a lot of antennas, but you don't have like enough electronics change. So you just switch some of the antennas off, and then you interconnect the electronics chain with the antennas that remain. And so on one hand, the antenna selection, and on the other hand, this notion of moving or reconfigurable antennas, where you're supposed to like mechanically shift around locations where the antennas are. Is there a connection to your work here between either of the two? I guess I'm not a huge fan of antenna selection, because to me it seems like you need a lot of switches, and these switches will come with losses, and these losses will translate into a hit on the link budget or on the received signal to noise ratio. And I'm not sure I'm a huge fan of the idea of moving antennas, because you need like a lot of mechanical parts that move around. Whenever you got a mechanical part moving around, you got something that somebody needs to make sure that it stays lubricated, and you're gonna get like cables that bend and twist, and over time they are likely to break. Like anything that you bend and twist back and forth over time will eventually break. But it sounds to me that there is a connection here between actually being able to reconfigure the topology of an antenna array for a specific site location, and these notions of antenna selection and moving antennas and so on. Could you speak to that, Emil?
Yes, so there is definitely a connection, particularly in the mathematics. So we sort of formulated to solve a problem where we said, let's optimize the average data rate over 10,000 different user realization. But if you bring that down only to one realization, here is my particular users, let's find the best locations of the antennas. Then you can solve the problem using the same tools, and you find particular antenna locations. And if you then have some hardware capabilities where you can move around your antennas in real time, well, then you could achieve that performance. And you should, of course, do better if you optimize for every user. Every time the users pop up and want to access data, you move the antennas to find the best location, as compared to deploying them once and for all.
Yeah, sure. But how large are the gains? I mean, what are we talking about here? Because I think to justify anything like a moving antenna arrangement, you would need to see gains of at least 3 or 4 times in capacity. Otherwise, it would just be worth it. So how large are the gains in your, did you simulate all these systems?
We definitely did that. And I mean, there are gains. And the gains comes from that when you position the antennas in this non-uniform once and for all way, you want to spread out the side lobe interference so that it is equal over all angles, while with the movable antennas what you can do is that you try to have as peaky side lobes as possible, and then you put the zeros, the nulls, in between them, exactly where another user is. So you can basically try to make the channels to your users orthogonal to each other. So you can transmit to any of them. They are perfectly isolated in space. They are not interfering with each other.
No, sure, but Emil, this requires that the users actually stay static in their location while you reconfigure the arrangement of your antennas now. So kind of like the time scale on which you shift around your antennas mechanically would have to be comparable to the coherence time or the mobility of the users, which seems to me that it might only work if, I mean, maybe for some sort of fixed axis where users don't move at all, I can see this, or if somebody moves, like is known to move very, very slowly, or at least, and you have a comparatively very fast like way of shifting the location of your antenna arrangement.
Right. And when you say coherence time, we typically refer to how quickly does it take from the channels to change so much that you would like to change your beam forming, and in this case change the antenna locations. But here one needs to distinguish also between non-line of sight cases where you have a lot of multipaths, and when the channel is changing, things are changing very drastically. While if you are in a line of sight dominant scenario, every user have a main angle. That angle shifts a little bit, but you need to relearn the channel, because in addition to the channel shifting, that rotates your constellation diagram at receivers. You need to relearn from that perspective. So those situations where you might not change
that could be
often.
handled. I mean, the rotation of the constellation is not a big deal. I think I know that can be handled just through a demodulation pilot, but it's more important to get the channel state information at the transmitter to actually know the angle in which you're shooting the beam.
Yes.
But you're right that in a line of sight, then the concept of coherence time becomes slightly different.
Yeah, so then the optimal antenna locations might stay roughly the same for a longer period of time. But I will now answer the question that you asked. How much do we gain from movable antennas? So
how much do we gain?
If you take an arbitrary paper on this topic and you look at the performance that they're showing, there is great gain. Sometimes they are doubling the performance. But then one should be careful with what are the things that they're actually comparing against. Well, they usually start with having the same number of antennas in a tiny, like half of a wavelength apart array. Then they stretch it out to the maximum size and have a sparse uniform array. And then they have the movable antennas. And there you see a progression going from small to sparse is better, and going from sparse to movable antennas is way better. But what they don't show in between are these non-uniform arrays that I have been preaching about.
Oh, really? So are you saying that nobody has investigated this in the literature? I mean, it seems like such an obvious thing that you could do. And long ago now, I think you and me had this conversation about why antenna arrays look the way they look, right? I mean, to start with, why do they have to be so ugly? That's one thing we can talk about, but let's forget that for now. Or let's not go there for now. But another thing is like, okay, why don't you could throw antennas out anywhere. I mean, you could, like the lights on a Christmas tree. Yeah, so you got the cable, and along the cable there are some antennas, and you just kind of like put it out there, and like a spider web, and would it even make a difference? And now you're saying that no, it doesn't it makes a difference, but it could even be that it's actually a lot better than putting the antennas with uniform spacing.
Yeah,
but it's quite interesting to know that. So you're saying that in the literature, nobody has investigated before, in fact, the performance gains of optimizing these placements.
Yeah, so I think we were the first ones to really compare these two concepts with each other in a few papers, including the ones that you were referring to and that we will mention in the description of this episode. And what we see then that if you're really comparing with an array that is optimized for this setup, then you might have some 10% gains from the movable antennas left. But as you were saying, that you will probably lose a lot of those gains in reality because of all kinds of hardware issues, and also because you need some deeper kind of channel knowledge in order to figure out how you want to move the antennas, because you don't want to move them around to a number of different sample points, estimate the channels, and then repeat a very cumbersome situation. So somehow you need to be able to predict, if I just move it there, performance will be better.
Yeah, sure. But that's such an important conclusion. I mean, so one thing you said along the way here also about channel state information, of course, I mean, once we depart from uniform linear or uniform planar arrays, I suppose reciprocity is the only reasonable and the only technically sound way of getting the channel state information. But back to the movable antenna, so if I understood you well here, your conclusion was that comparing a movable antenna configuration with just an optimized non-uniformly spaced array, the gain you could get is like 10% in typical situations. And to me, who cares about 10%? I mean, it sounds like there's no way that that's going to be worth it. So important conclusions, I think, Emil, in your new paper.
Just for the record as well, some people are calling movable antennas fluid antennas. That means basically the same. It all goes back to different ways that one could implement things. You were mentioning one could implement movable antennas with antenna selection type of technology. It could be mechanically moving, or fluid antennas, just describing that every antenna is an electrolytic fluid antenna, that where you can change its properties by changing something within the fluid's properties. So yeah, there are many terms. People are fighting right now about what to call it.
I see. Yeah, sure. All right. So in wrapping this up, Emil, how do you think that antenna arrays and panels eventually will look like for 6G and maybe beyond? I mean, let's say for the future.
So,
or in the
so I think the first step that will happen in 6G is that we will go from the frequency bands 3.5 or C-band that are typically used today for the state-of-the-art 5G systems to something around 7 to 15 gigahertz, called the upper mid-band. And when you go up in frequency like that, the wavelength is shrinking by 2 to 4 times, and that means that within the same size of a base station, you can squeeze in many more antennas. So you could have maybe 4 to 10 more times more antennas inside the same box. But that is the issue that I'm seeing, that you don't want to scale it like that, because then you would need to have so much radio hardware behind it. And that gives you then the opportunity to not have uniform arrays anymore, but within that box, play around with the arrangement, use this kind of concept that we were talking about in order to provide better performance with a reduced number of antennas. But you still need to be careful with maintaining your link budget, and so you can do that by having antennas possibly with some different gains, or play with the gains of them, aim the radiation gain so that you have a wide coverage of each antenna horizontally but less vertically, for example. There are also some more futuristic ideas about putting a transmissive reconfigurable intelligent surface, the things we talked about in a recent episode, in front of the array to collect all the energy that hits the array, and then analog beamform it towards your fewer number of antennas at the backside of your antenna arrays.
I see. I mean, it sounds like an advanced electromagnetic lens somehow, but maybe let's not go there today. But so my understanding now is then that the operating point of interest here for array topology optimization is really when we've got the physical space, okay, or rather this way. So we got a nominal design, which is a compact array with lambda half or half a wavelength spacing. Typically would be like a mini rectangular or array. But then we've got the physical space. so that we could actually stretch out the aperture. But we can't afford numerically more antennas. And then the question arises as to, well, should we place these antennas now with larger than half a wavelength spacing uniformly, or on some kind of grid, or just at arbitrarily, maybe even random, or at like arbitrary or perhaps optimized locations? And if we do that, how large are the gains? And that is basically what you've been addressing in your papers here. So very interesting question, I think. And I also think that there are other considerations that we need to make. One is that while in principle it's a great thing to enlarge the aperture, and your antennas might sit more sparsely together. I mean, it's a good thing, because a larger aperture means better angular resolution, means a sharper main lobe of your beamforming and so on. But it also means that signals within the array have to travel a longer distance. In particular, if you got RF oscillators, or PLLs or whatever that drive the antennas, and you feed them with a clock, then the cable that feeds the clock has to be longer, so the losses are going to be higher. And also all the digitized baseband and all of that will have to travel further. So there will be implementation challenges here that probably eventually determine, I mean, it's not only the availability of physical space, but it's also the cost and the power consumption and the difficulty of building the actual electronics that will determine how large apertures that we can eventually feasibly build. And this is a trade-off and a topic that I have a bit of a hard time speculating about, because on one hand I can see the desire to build a compact array for the electronics design, from the electronics design perspective. I can see the desire to build a physically larger array with non-uniform antenna spacings from a com-theoretic perspective, as you demonstrated in your paper. And I guess only the future can tell what the next or the future lines of products here will look like.
Yes, and if one can solve that clock distribution problem that you described, then one potential way of deploying base station in the future would be that on the same rooftop, you don't deploy one antenna panel but you cut your panel into multiple pieces and you move them apart. And
multiple small panels.
Multiple small panels.
Within every little panel, you might have like a small compact array or something.
And then when we were showing that concept in some papers, we put them out in just a uniform manner there as well. But potentially they should not be uniform. The first one should be 1 meter apart, and the second one should be 4 meters apart, just to get further information into the system and reduce the redundancy.
Right. Sure, yeah. And of course the eventual solution would be to just spread all the antennas out as far as possible, and that would be the DMIMO or cell-free MIMO concept. That's the ultimate solution, I think.
But even then, we know that it might not be a random distribution, but maybe you also want to optimize the location for some kind of
optimize the locations. Great. So that sounds like in fact, a gold mine of new physical layer research problems that have been largely untouched in the previous literature.
Yes.
Yeah.
All right. So I hope that some of our listeners will get inspired and consider some of these things in their own research or studies in the future. So with that, thank you, Eric, for a great conversation today, and thank you to our listeners, and please like and subscribe and watch our next episode.
Thank you, Emil.